All right, here, hey guys. So I wanted to make a quick video that discusses the Jaseci concept, and this is just for internal people to understand what we're all working on and what we're all building. So this is gonna be relatively high level, but I'm gonna map it to understanding the landscape. So let me just get this set up real quick. I created a diagram that could be helpful with this objective. So basically, so this is the Jaseci stack, right? So we all remember when Jaseci was essentially an open source project, right? It itself was a piece of software that we were developing in an open source way. Well, we've evolved that mission. We've evolved that packaging, right? So Jaseci now refers to the technology stack that is comprised of multiple pieces of technology. So this is in some ways inspired by how LLVM organizes its repo and organizes its project. There's actually multiple components that are kind of constituent parts of an LLVM stack, Clang, the the LLVMIR, etc. There's a number of individual components that represents an ecosystem of software that often these things can be used in a self-contained way. But really, it kind of represents one coherent, consistent ecosystem for building compiler infrastructure. So Jaseci is kind of organized that way, where Jaseci is the name of the stack. It's the name of the ecosystem. And it's a lot like LAMP, right? Where you have a LAMP stack that includes constituent components. So let me just talk about conceptually what Jaseci is. So Jaseci comes from a thesis that the way we create software has stagnated since the 80s. We're still using traditional programming languages and programming interface to the computer to construct software, and we cobble together these abstractions through highly complex lower level abstractions. So many examples of this is if you want to write a piece of software that represents a neurosymbolic expression of the software, which means that it's on the critical path of executing the software or running the software, that there's parts of the problem that the software solves that requires both traditional symbolic code. So that's the code you write, if else statements, control flow logic, the logical expression that we are used to. And then there's also a constituent part of realizing the software functionality that requires an AI model, which doesn't really function in this logical rules-based if-else statement. So that's one of the important ways we write software today, and it'll continue to be an important way that we write software into the future. Another really important way that we write software is where it's set up to be cloud native, right? So there's a notion of persistence that goes across entry points of a program. Now, I'll link this conceptually. When you build a server that has REST APIs, essentially each one of those APIs is an entry point to the program. It is like a main function in C, or the whole script in Python. The whole module in Python is almost an entry point in and of itself. However, software going forward has multiple of these entry points that you can invoke through an API, and there's a notion of persistence that goes across one invocation. When you run a request, it's almost like you're invoking the software, and that request can come in from multiple entry points, multiple disparate API points. This is a standard way that we write software, and indeed, like when you look at how APIs are developed now, we by and large, at least in the Python ecosystem, will just write our Python program and decorate the functions to be those entry points. So the primary model for executing that program is not running the module. It's actually making these API calls to multiple disparate entry points that can each be invoked in the standard execution model of the software, right? So this is somewhat technical, but those are abstractions that are not present in programming languages. Turning a Python program or a C++ program into a server requires complexity that is essentially handling this distinction between having multiple let's say, abstraction level entry points to the program or not. Now, when we create a programming interface or a programming model that has language level constructs that present these semantics explicitly in the language, that creates simplicity when it comes to building software. And so things like whether or not something becomes an API can be automated when that's done at the language level in a simple way. So that's another example of an abstraction. When it comes to this neurosymbolic realm, the code constructs introduced by the MTLLM project in Jack Lang is a new way to reason about how we write these neurosymbolic programs. And so, and there's a number of these abstractions. That's just examples of abstractions that kind of brings the way we code into the future. And the hypothesis is we can reduce the complexity of creating software while allowing smarter engines to automatically optimize that software for the hardware we have today. So that's the ultimate goal of Jaseci. It's really a thought process, and it's actually a very ambitious project that tries to realize this for real production grade software, which we've had a good bit of success with through Jaseci 1 and Jaseci 2. It's reinventing the whole programming stack with higher level abstractions and more opportunity to automate and let the runtime make decisions as to what are our microservices. How should we prompt a neural network model? One of the interesting theses of this project is that prompt engineering is ultimately going to go away. We're constructing the research paper that provides evidence for that, which we plan to submit soon. But imagine not having to do the complexity of prompt engineering on the critical path of your software development. And that's also automated by the runtime of this stack, right? So a lot of these are very, very new cutting edge ideas. Anyway, what I want to do is talk a little bit about this diagram that's on the screen. So this diagram shows conceptually, on the left side, we have the conceptual view of a Jaseci stack. And then on the right side, we have the constituent open source projects that we are maintaining that realizes that stack at production grade. There's currently multiple commercial products built on this stack that we're really proud of. And some of which run on Jaseci 1 still and needs to be migrated to Jaseci 2, and some that run on Jaseci 2 today in production. So the right side is the software projects, and many of the folks listening to this are contributing to some of these, to some or multiple of these individual repos that constitute Jaseci's implementation of a Jaseci stack. So the Jaseci stack goes all the way from the programming interface abstractions down to the device level abstraction, right? So this is the hardware interface. And the entire design space of a Jaseci stack includes all of the software that goes between the language code being executed and the underlying device. And inside this box, there's a number of constituent software tooling and runtimes that are necessary to write and run these programs. At the programming interface level, this is a beautiful part of the design space where we can create the abstractions themselves at the language level that can be new abstractions that make easier articulating how the software should work. And it also gives us a way to hide complexity that developers engage today that we're dealing with, right? Like deciding our API ecosystem and creating, using all kinds of LangChain DSPY backflips to try to get models to do what we want on the critical path of the software, right? So a lot of that complexity, we're able to create abstractions that hide it, so we don't have to think about it. Beyond that, it also allows a runtime to make smarter decisions because the runtime can optimize the configuration, change the way that software functions at runtime and in response to runtime information, which isn't really something a programmer can do because statically a programmer has to anticipate all of the runtime scenarios that a programmer might want to optimize these kinds of choices for. Okay, so you have a compiler. This compiler is what lowers the Jack language to a lower level that can be further optimized to ultimately run on an interpreter or in the machine at the conceptual level. Of course, in our implementation stack, we superset Python to realize this. So we target Python bytecode, and there's a lot of good reasons for that, thoughtful reasons for doing a native superset of Python. Python is the stack that most AI applications and modern applications run on. When you think of PyTorch, when you think of TensorFlow, when you think of Hugging Face, Ollama's ecosystem, these are all Pythonic ecosystems. The compilers, most of the compiler research when it comes to accelerating production grade acceleration of models is starting to JIT Python bytecode, which is what we target and which is what's in our compiler toolchain. So we have the Jack compiler. There's an automatic cloud native runtime. Some of these abstractions allow you to write a program without reasoning about whether it's in the cloud or not. Two of these abstractions is the notion that there's a code construct that represents more than one entry point of a program. So you don't even have to think about like doing that. Basically, you've got, of course, functions and classes, which are traditional, but you have a notion of a walker, which inherently just represents multiple entry points. You can start your program from any walker, right? And it's basically it's a very simple abstraction. So that's one that's a cloud native abstraction. The other one is the notion of persistence across runs. And so that's built into the language natively. From the 80s, most programming languages will use like files or an explicit DB library to capture persistence across runs. However, this is a language level abstraction, and it's from the root node, for anyone that understands that, that allows you to not even think about schemas and protocols and interfaces for how you make persistent data across runs. So those are two abstractions, and the cloud native runtime is the code stack that does the automation around turning those two language level abstractions into your program can run on a single command line terminal on a single machine, and the same program without changes can run in a cloud and be distributed across 1 million machines with 1 billion users, right? Calling your walkers from anywhere. So that's all hidden. The complexity to that is hidden and automated by this runtime. And the runtime can then make changes to how data works and what's cached in memory, and all of this complexity you don't need to worry about at the program level. So that's the automatic cloud native runtime. There's also a neurosymbolic compilation. Really, I should probably put a bigger box around all three of these to really call it the compiler stack. But we also have this notion of neurosymbolic compiler passes. This is some novel stuff. We're creating a semantic IR, and this is an IR that's designed for LLMs and generative AI models to be able to reason about. And it's specifically IR for the interaction with LLMs on the critical path of a piece of software running. And so there's a couple projects that's related to that, MTLLM being one, but also AI asserts, what I'm calling AI asserts, where when you have an assert in a running program, an LLM can understand not just the static state of that program, like the code or the semantics in the code, but also the dynamic bindings to variables and like what that means. And so this IR can maintain semantics, not just in the static realm, which is kind of common today. When you cut and paste code into ChatGPT, you're really experiencing a semantic realm reasoning of that program, but also in the dynamic realm. At the point of a assert occurring, it can see the values throughout your semantic code and then reason about why that assert happened. That's another use case for this kind of neurosymbolic compiler. The first use case, the MTLLM use case I mentioned, is really where you can automate the translation of symbolic, traditional code structures and constructs to more semantic constructs. Automating that. Essentially, that means prompt engineering. So where you can have a runtime automate the prompt engineering and simply use function signatures, let's say, to then infer what actually you want that function to do without a user having to design prompts in and reason about responses out. And that's actually another use case for this kind of newer symbolic compilation infrastructure. We also have this notion of automatic micro-splicing engine, which is JSORC. And this is essentially realizing that at the module level, we already have an abstraction, especially with this kind of multi-entry Walker concept, right? We already have an abstraction at the module level of what should or shouldn't be microservices. It turns out that when you build your microservice today by hand, you're essentially in practice, at least in the Python ecosystem, writing a Python module and then doing complex things to that module so that it functions as a microservice. And so that can be automated. That can be hidden, where you can just write your Python program with its standard, like as if you're prototyping it on the command line. Of course, it's in the Jack expression. And that program and this runtime can automatically make decisions as to what should be, how should that Python or how should that application that's written simply be sliced into microservices to communicate with each other, and then how those decisions can be changed dynamically in situ as the application is running based upon the behavior of the application. What are the requests? What are demands? What are the bottlenecks in the microservice deployment? And so that's a separate engine that does that. And we've prototyped all four of these things are either in production running for commercial applications or prototyped and validated to be effective. And so what signifies the dotted lines represents things that are not running in production right now with commercial products, and the things that are dark are running right now with production products. So that's what the right view of this world means. But there's already validation prototyping for JSORC, and we're working on turning JSORC into a real sub-engine of this ecosystem, which is super exciting and incredibly novel. The last thing I'll talk about really is part of this compiler side of the world, and that is the AI model compiler, which can be integrated into this runtime, this Jaseci stack. So that is there's a number of basically at the end of the day, when you're running an application that has AI on its critical path, you're going to need to map that AI to accelerator hardware. It's just a fact because it's compute intensive and you need specialized hardware for AI inference. Now, there's a number of systems that already do this, and primarily the systems that are modern, the way they do this is by just-in-time for eager mode models, let's say, which is like PyTorch 2 style models. The way they achieve this is by, and they achieve performance is by just-in-time compiling Python bytecode. And so that you can map that to you can be efficient in mapping your work to the accelerator hardware. And today, those kinds of systems are limited by the abstractions that's present in Python. And it's limited by these abstractions that are from the 80s, right? Which is what Python really captures, right? And so, so there's a design space to expand upon, to dramatically expand upon those set of abstractions if we were to co-design that with the full compute stack, this full Jaseci compute stack, because there is information that is relevant from the abstraction layer that you can statically use to plan how your end-to-end compute will map to accelerator versus general purpose hardware, right? And so that's an integral part. For example, using some of the data spatial semantics, that's another way you can articulate an ego mode model inference. And then those data spatial semantics also have concrete guarantees as to how much data is accessible at each program point in an incredibly strict way, which means that when you're mapping that to accelerator hardware, you have more guarantees that allow you to make aggressive decisions as to how you plan that compute. So you don't have to be conservative because you don't know what the general purpose aspects of coming back to Python land might impact. And so you don't have to make conservative decisions for functionality because you have these constraints around what is expressible in data spatial articulation of the, say, model inference, or the model architecture, I should say. And so like that's some of the design space that we now have available when we integrate this into the compiler toolchain of a Jaseci stack, right? So yeah, anyway, and some of these, like this will be updated, right? Because there's actually a runtime. There's a runtime that's missing from here, but that's, you guys would know it as jacklib. It's actually in this one. This is really jacklang and jack RT lib, right? Because this runtime is actually present as you're interpreting, as you're executing your jack code. So I'll figure out a way to put that in this box. It's actually it's a subset of the jacklang project or repo. But that is Jaseci, right? That's the vision behind Jaseci. And so at the end of the day, we should have two successful, we have two goals. The first goal is to make the creation of software much simpler, reduce the complexity drastically when you want to articulate an application. And that lowers the barrier to entry for people who want to build software that can scale to millions of users, is highly performant, and for which they don't have to reason about and understand all of the complexity involved in using a more traditional view of the world that's a little, has stagnated. So that's one goal. Anybody can write amazing software with much less complexity to reason about. The second goal is also, we can empower the runtime to make both static and dynamic optimization decisions with a new realm of control as to how the software maps to hardware or maps to a cloud. And change those decisions, like what are the microservices? Those microservices are dynamically decided and can be dynamically changed to bring certain services together into a more monolithic element, and vice versa. That's one example. Another example is you can optimize the prompts or reason about the prompts in a dynamic way. It turns out that every model you use, various prompting decisions become different and relevant to achieve the goal. The goal could be expressed incredibly simply, and the semantics of the code itself and the call sites, let's say, to the LLM can provide ample information. However, the complexity that comes from getting the prompting right, that also can be optimized dynamically as your program is running, let's say in a cloud environment or offline. So better mapping and optimization, the goal number two. Goal number one, drastically increase simplicity and higher level abstractions, which is really how we make progress in developing. If you think about all the progress we've made in computer science, it's from raising the level of abstraction. And now it's time to raise the level of abstraction yet again in this new world of software creation. We did it before from literally bits and punch cards to assembly language. Go-to statements was a huge, and labels was a huge abstraction in assembly language. We did it from assembly to Fortran and C, where we had functions and structs, incredible abstractions that moved the science forward. We did it again when we created object-oriented programming. We did it again when we did automatic memory management, where you didn't have to manage your news and deletes or mallocs and frees. And then now it's time to do it again, right? And so that's the endeavor of Jaseci, and we're doing it for real with real software running on this stack. We're doing it in a way where it natively supersets Python. So you literally can eject your Jack application into a set of Python code and libraries, right? Pure Python. So we're doing it in a native Python superset way. And we intend on building amazing software and providing this to anyone who wants to write amazing software from now into the future. So that's the that's kind of the Jaseci world. And, you know, very excited to continue this awesome journey. We've already achieved so much. And I look forward to achieving more. Anyway, I thought I should put this together just so there could be one central place that people can understand, like, what is Jaseci? And cool. Feel free to reach out, ask questions, and we'll talk again soon. Awesome. Later.